Welcome to this explainer on mastering Apache Spark. Look, today we're going to take you from being just a theoretical learner to a totally confident, interview-ready Spark practitioner. If you've ever pulled your hair out over a job that just refuses to finish, or maybe you felt a bit overwhelmed by the absolute mountain of Spark terminology, well, you're in exactly the right place. We're going to break down this complex architecture into clear, visual, and most importantly, highly actionable concepts.
To really grasp Spark's complex architecture, let's start with a surprisingly simple, brilliant analogy. Just imagine an incredibly busy restaurant kitchen. Every single component in there has a very specific, crucial role, right? The driver? Well, that's your head chef. They aren't in the back chopping onions. They're the ones coordinating the orders. Then you have the cluster manager. Think of them as the manager assigning the actual kitchen stations and handing out resources. And the executors? They're your station teams. They are the ones actually doing the heavy lifting and cooking the food. Now, a shuffle, and I know, that's a term that strikes absolute fear into the hearts of data engineers. A shuffle is really just that chaotic, expensive moment when ingredients absolutely have to be moved between different stations just to get a dish finished.
Here's our roadmap for today's explainer. First, Spark's core mental model. Second, the execution flow story. Third, diagnosing Spark bottlenecks. Fourth, optimization and tuning. And finally, cracking the Spark interview.
All right, let's jump straight into Section 1, Spark's core mental model. So, at the very heart of it all, Spark splits its responsibilities between the driver and the executors. The driver is the brains of the operation. It runs your main code, builds out the logical execution plan, schedules all the tasks, and tracks the overall progress. But, and here is a really critical warning directly from our source material, if you use a command like collect on a massive data set, you're literally forcing all those worker executors to send their massive chunks of data straight back to this one single head chef. And what happens? The driver's memory gets completely overwhelmed and your application crashes. And that happens even if your workers are perfectly healthy. On the flip side, the executors are the muscle. They run the tasks concurrently, they cache the data, and they report their metrics right back to the driver.
Now, to really master this, you absolutely have to speak the language of Spark. These aren't just random buzzwords. They actually form a very strict hierarchy. It goes like this. An application is your complete program. Within that application, a job is actually only ever triggered when you call an action, so things like count, collect, or writing to a file. Once triggered, Spark splits that job into stages. It does this wherever data has to be redistributed across the network. Those are your shuffle downeries. And finally, each stage is divided up into tiny units of work called tasks. Each task processes exactly one partition, which is just a single slice of your distributed data set. So memorize that flow. Job to stage to task to partition.
Moving right along to Section 2, the execution flow story.
What's super interesting here is how Spark actually handles your code. It uses this concept called lazy evaluation. Basically, when you write transformations like a filter or a select, Spark doesn't actually process the data right then and there. It's lazy. It waits for an action. But once that action finally hits, Spark's Catalyst Optimizer kicks into high gear to refine your logical plan. It pushes filters down to the source, it prunes out unnecessary columns, so you're doing way less work. Then it splits this newly optimized physical plan into stages right at those shuffle boundaries we just talked about, and finally, it actually launches the tasks out onto the executors.
Let's actually put some real numbers to this so it makes sense. Say you have a 1 terabyte dataset, and it's grouped into 400 post-shuffle partitions. Well, that equals exactly 400 tasks. Now imagine you're on a cluster that has 100 executor cores available to you. Those 400 tasks are going to run in roughly 4 scheduling waves, literally just 400 divided by 100. Understanding this basic math makes it so much easier to see why partition sizing is pretty much the ultimate lever for controlling your cluster's parallelism.
Now, the speed of those scheduling waves depends heavily, and I mean heavily, on the type of transformations you're using. Narrow transformations like your basic select or filter are incredibly fast. Why? Because each output partition depends on just one single input partition. They can just be pipelined together on the exact same machine without moving anything across the network. Wide transformations, on the other hand, things like group by or distinct, those require a shuffle. They literally force data from tons of input partitions to be moved all across the network just to form new output partitions. Look, shuffles aren't inherently evil, they're often totally necessary, but minimizing them, that is the absolute secret to a lightning-fast pipeline.
All right, let's get into Section 3, diagnosing Spark bottlenecks.
When things inevitably slow down, you've got to play detective. By looking at the Spark UI, you can actually map specific symptoms directly back to their root causes.
For example, if you're looking at the UI and you see most tasks finishing up in, say, 40 seconds, but a handful of tasks are dragging on for 20 minutes, that symptom points straight to data skew. It means one key has way too much data. You'd probably want to fix that using adaptive query execution or AQE skew handling. Or what if you see hundreds of thousands of tiny little tasks and a massive scheduler delay? Well, your partitions are way too small. You need to coalesce. And if you're hitting out-of-memory errors or seeing heavy spilling to disk, that means your partition's working set is just too large. In that case, you actually need to increase your partition count to give each individual task a bit less data to chew on.
The absolute most crucial point here is that optimization is not about guessing. It is a controlled investigation. You really need to follow this specific diagnostic loop. First, you capture a baseline run. Next, you inspect the SQL plan and the UI. Then, you classify the bottleneck. Are you constrained by CPU, the network, or memory? Once you know that, you form exactly one hypothesis. You apply the smallest possible change to test that single hypothesis, and then you meticulously measure the result. Think about it. If you change 5 different configurations all at once, you are never going to know what actually fixed the problem or honestly what brand new problem you just introduced.
Next up, Section 4, Optimization and Tuning.
Okay, so when you are adjusting your partition counts, you basically got 2 main tools in your tool belt. First is repartition. This triggers a full network shuffle. Yes, it's expensive, but it gives you a perfectly balanced redistribution of your data, and you can use it to either increase or decrease your partitions. Then you have coalesce. Coalesce usually just combines existing partitions that are already on the same machine to reduce the total count. Because it avoids a full shuffle, it's way cheaper. But, and this is a big but, if your data was already imbalanced to begin with, coalesce might just preserve that exact same skew.
Join strategies are another massive tuning lever. A broadcast hash join is absolutely brilliant when one of your tables is small enough to just fit right into memory. What Spark does is take that small table and broadcast a complete copy of it to every single executor. This totally avoids shuffling your massive table across the network. It's great. But if both tables are huge, you're going to have to rely on the sort merge join. This is basically the highly scalable workhorse of Spark. It does require both sides to be shuffled and sorted, which takes work, but it can handle virtually any volume of data you throw at it.
This all brings us to the high-leverage optimization hierarchy. Before you ever even think about touching advanced hardware settings or just blindly throwing more executor memory at a problem, you need to follow this specific list. Priority 1, read less data. Use partition and column pruning so that extra work is removed before it even enters the engine. Priority 2, use efficient columnar formats like Parquet. Priority 3, reduce network movement by filtering your data as early as possible. And Priority 4, balance the work by addressing data skew. Seriously, only after you've exhausted all these logical fixes should you even consider tweaking your cluster resources.
Finally, let's wrap up with Section 5, Cracking the Spark Interview.
The absolute most effective way to answer any Spark architecture or tuning question is by using the rule of 4. Step 1, state a simple definition. Step 2, explain the underlying mechanism, like how it actually works under the hood in the engine. Step 3, give a concrete, real-world example. And Step 4, always highlight the trade-offs. So for example, if an interviewer asks you about caching, don't just sit there and say, oh, it makes things faster. Say that it stores intermediate results. That's your definition. Say it stores them in executor storage memory. That's your mechanism. Mention that this is fantastic for iterative algorithms. There's your example. But it consumes memory that could otherwise be used for execution, so you absolutely must unpersist it when you're done. Boom, you've captured the trade-off. Doing this proves you're a real practitioner, not just somebody who memorized a dictionary.
Above all else, whether you're sweating it out in a high-stakes interview or dealing with a massive production outage at 2 a.m., you need to explicitly communicate that you look at the evidence, you look at the physical plan, you look at the Spark UI. You rely on stage-level metrics before you ever start blindly changing configurations and just crossing your fingers hoping something works.
So, as you head back to your own clusters to tame your big data pipelines, and as you get ready to absolutely ace your next technical interview, I want to leave you with one final very important question to ask yourself. When a job fails, or when it crawls to a halt, are you tuning by evidence, or are you tuning by superstition? Thanks so much for joining me on this explainer. Keep learning, keep measuring, and we'll see you next time.